All right, so we are talking about electromagnetic induction today. And there was a sentence up here that I erroneously placed. It says the law of electromagnetic induction. It's this yellow highlighted sentence here. Is a current can be induced into a conductor whenever the magnetic field in its region changes, right? That's actually Faraday's law, and our textbook calls it, or sometimes it's called the other way around, or whatever the case. It says a changing magnetic field can induce a current in a wire, essentially. It's kind of the idea, okay? Induced means you're sort of producing a current in a wire, right? So, if I've got like a wire in this particular area, let's say I've got just sort of a looped wire here, like this, and goes, I'm going to try and do a loop. Oh, am I going to be able to do it? I did it. There it is. There's a loop. And then on the edge of this wire, I've got maybe something that can measure the current. It's sometimes called an amp meter. Okay. Now, if I've got a magnet here, all right, and let's just say that this is north and that's south, what's going to end up happening is nothing until this magnet actually starts to move, because it has to be a changing magnetic field. So when the magnetic field is stationary, it's not changing, right? So therefore, what ends up happening is nothing until I move this. So if I push this magnet in like that, for example, or if I even pull it out like that, then the magnetic field is changing, right, at that point, because the magnetic field around this magnet is here. And then if I push it in like that, then this field line, which was here, would move closer. And therefore, this wire is then in what is called a magnetic field, okay, that is changing. What ends up happening is you get a current that then flows through this wire, and it's either moves in that direction or that direction. Now the direction of the current is determined by Lenz's law. So these two laws together basically make up what's called the motor principle, okay? Faraday's law says that a changing magnetic field induces a current in a wire, okay? Whereas Lenz's law says that that current in a wire that gets produced is in a certain direction. And that direction is a direction such that that current creates its own magnetic field, which opposes the magnetic field that created it. Okay? Holy moly. So let's see what that's going on. So let me draw up an example here. So I've got now, let's say, a coil here. And let's say that this coil is, oh, shoot, I erased my coil. A cylinder, and it's hollow. Like this. Okay? And then I've got a thing to measure the current here. Now, I've got a magnet that's north here. If I push this magnet in this way, okay, what's going to happen is this wire will get a current in it because it is now in a magnetic field that's changing. Okay, that current will push along through the rest of these wires as well. Okay, and what ends up happening is, well, this wire, the current has to decide, is it going to go up and around that way, or is it going to go around that way? Well, it depends on whether or not I've pushed this thing in. So let's say in this case, I've pushed it in. If I've pushed it in there, then what's going to end up happening is this electromagnet, which is this thing here, it's going to turn into a magnet, and it's going to be north here and south there. Because the magnet gets created must oppose the magnet that created it. All right? And this has to do with the fact that there's no free energy. Okay? So imagine I push this thing in here, this magnet, and it's going to feel some sort of resistance because remember, north poles and north poles don't like each other, right? And so basically what's going to end up happening is now if I take my right hand and I wrap my fingers around like this in my right hand because my thumb is pointed that way. Remember the the right hand rule for electromagnets or coils. My thumb points north, and therefore my fingers wrap around in this direction, towards the front of the electromagnet. All right. And basically what ends up happening here is, therefore, I know that my current is facing in the direction that I just did not erase there. So my current is going to go down the front here because I'm pushing a north magnet into here. Okay. If I push a north magnet into there, right, then a north magnet gets created because it wants to resist the motion that I push. Why would it want to do that? Because, well, imagine pushing a north magnet into here, okay, and imagine it created a south, right? If I were to push a north in and it created a south, what would happen? What does a north and a south magnet do to each other? They attract each other. So basically what would happen if this were true? Now what I'm saying is not true. If this were true, then a north pushed towards an electromagnet creates a south, then therefore this magnet would say, oh, look, now I really like that south. And so it would actually get pulled in because it created this south. And then as it gets pulled in more, it would create a stronger southern magnet. And so as a result, all you would have to do is just barely push this magnet 1 little millimeter, and all of a sudden it would create a southern magnet, and then it would move the rest of it the way all by itself. And you would basically be getting what would be called free energy, right? Free motion. You would get free kinetic energy because this magnet would get pulled in by this southern side, which got magically created by the fact that the north was created. But there is no free energy. And so, therefore, this ends up not being south, but it ends up being north. Okay? Then likewise is true in the other direction. Let's say instead of pushing this magnet, I pull it away. I pull this magnet away. Okay? If I pull this magnet away, then a north won't be created here. Because if I'm pulling the magnet away, what happens between north and north? They get they repel each other. So if I pull this magnet away, then what ends up happening is not a north, but a south here. Because imagine if a north got made. If a north did get made, then I would just have to push it away just a little bit, and then the rest of the repulsion would happen because it would get pushed away by the fact that a north magnet now exists in this location. But it's not the case. It's going to be a south magnet. And so basically what ends up happening here is in this area, sorry, I'm trying to erase this. There it is. There we go. I can create a north or a south by either doing one of the two following. So if I pull this away, basically, then a south gets created, right? If I push it in instead, then a north gets created. Okay, so now let's talk about this. Basically, the idea now is that with this action, the idea of pushing and pulling a magnet back and forth, all right, imagine doing this just back and forth, push, pull, push, pull, push, pull, right? Then basically what I've effectively done is I've switched this from a north to a south back again over and over and over again as fast as I can do it. And what I've effectively done is I've created a current in this wire right here that ends up oscillating back and forth, back and forth. Actually, it ends up alternating back and forth. And so I get essentially an alternating current over here, and where I can maybe attach maybe a light bulb where I can light up a light. Okay? And this is the concept of how a generator works. All right? A generator. So basically, I take a magnet and I push it back, push, pull, push, push, pull, push, pull, push, pull, back and forth, and I basically can create a current that oscillates back and forth that can be used over in another location to run some sort of electronic device. I have generated electricity, and that is Faraday's and Lenz's law, right? Likewise, rather than me pushing and pulling the magnet, okay, if I instead take a current and oscillate it through here. So I've got a current and I oscillate it through left, right, left, right, left, right, left, right, left, right. Then basically what I can do is I can have this thing alternate back and forth between north and south. And then I take this magnet here and I put it on a thing that allows it to rotate. Imagine this magnet can rotate back and forth like this, back and forth around. All right. And basically what happens is if I push a current through here and I make this guy north right now, then this northern magnet would want to rotate down, because he doesn't like that, because remember, this is on some sort of a rotating platform, okay? And therefore, the south magnet is going to rotate in like this. And it'll rotate around until all of a sudden the south magnet gets to this side and the north magnet gets to this side. And this is a permanent magnet, this rectangle here. So now all of a sudden south is here and north is there. And the magnet's like, yay, I'm really happy because this is north, and now my southern side is really close to a north side, and everything is all right. But then as soon as that magnet gets there, you, as the person in charge of this current here, switch it. So then all of a sudden, this no longer becomes north, but it is all of a sudden south again. And this southern side of the magnet is like, oh, shoot, you were just north and now you turned back to south. You tricked me. And so I'm going to keep moving this direction. And so therefore the south ends up going back over to this side. And the north comes back over to that side. And when he gets there, it's south again. And he says, oh, this is great. Life is good. Everything is fine. And then all of a sudden we say to ourselves, the north got here to the other side. I'm going to switch back to north again, you silly magnet. And there, all of a sudden, this magnet gets forced back in the other direction again. Okay. So as a result, what you end up getting here is a scenario where you can rotate a magnet around on a singular axis by alternating the current back and forth. Okay. And the speed at which the magnet rotates is dependent on the rate at, you can make it so that you can make it so that it's dependent on the rate at which you alternate the current as well. So different various frequencies and things like that. Anyway, so that's pretty spectacular. This is what's called the motor principle. Okay, the motor principle. All right. So together, these two principles were some of the greatest discoveries in humankind, in my opinion, and many other people's opinion. That and the transistor are some of the greatest discoveries ever, is that you can generate electricity with a spinning magnet, or you can spin a magnet with our electricity that's already been generated. And what are spinning magnets cool for? Well, you can run drills, you can run drill presses, you can run fans, you could run air compressors, you could run pretty much almost anything that requires a motor to run. Okay, so together these are called Faraday's law and Lenz's law. All right, and it has to do with changing magnetic fields adjacent to wires, and these changing magnetic fields push a current through the wire. Or if you push a current through a wire, you can push around magnets the other way around, okay? And together, that is called an electromagnetic induction, or the motor principle, or the generator. Sometimes a generator is called a dynamo, all right? That's one of the first words for it. And there you have it. Okay, so there's a couple of practice things on that, and that's the electricity unit right there. I'm going to go ahead and post this video, and at this point we've finished the electricity unit. You can kind of start taking a peruse through the textbook, and I'll send you a couple of other worksheets, and you can then maybe start looking at signing up for a test in these next few days, or by sometime this week or something like that. Okay.